So it's currently the 26th of March, 10:14 p.m. here in Sydney, Australia, and this is the countdown timer for the drone contest closing date. And this is for the entries based on the globe. We have 1 day, 12 hours and 45 minutes remaining, at which point I will list all the entries and put the winner to a vote. Now, I'm very happy to say that I have already seen several entries that satisfy every element of the challenge. And some of the solutions for demonstrating the equatorial mount were quite ingenious in their simplicity. This one, for example, uses a small equatorial mount just built with the Lego, and yet it demonstrates the operation of the equatorial mount polar aligned on a globe perfectly. So in about 36 hours, this contest will come to a close, and I'm very happy to know that I will be giving away a Mavic Pro drone and a P900 camera, because we already have more than 2 entries that satisfy every element of the challenge. So once again, thanks for taking the time to produce an entry, and good luck in the contest. So on occasion I get invitations from Flat Earth channels to participate in Hangouts, and it's not something I have done, and generally I'm not interested, as I prefer to do my own thing and make my own videos. In the last week I have received 3 separate requests, so just be aware, guys, that if I'm going to join you in a Hangout, the topic I will be discussing is long-range international flight plans, because this is something I have done personally for over 30 years. I have 10,000 hours of actually flying real aircraft around the real Earth, and I can produce flight plans from any location on the Earth to any other location in the space of minutes. Now, this friendly challenge to flat earthers to produce a simple flight plan based on the flat Earth has been unanswered for more than 15 months. So if you want to engage me in a Hangout, you need to show me that you are capable of producing a real aircraft flight plan. I'm not talking about drawing lines on an AE map with crayons. I'm talking about producing an accurate flight plan that can actually be used in a real aircraft, that has fuel calculations, accurate distances, waypoints, course directions, distances, time intervals, and fuel estimates. So this is something that I can do easily. I have spent my life flying around the real Earth, producing flight plans myself using raw math. If you cannot do that, there is no point inviting me to your Hangout, because we will be stuck on the first topic. So the last part of this video is a demonstration of how we calculate the takeoff speeds using the flight management system on board the aircraft, and how the weight of fuel on board the aircraft will significantly affect that speed. I made this video today at the aircraft, and in future videos I'm just going to cover off on different aspects of aircraft operation and flight planning, and this is the first in that series, showing you how aircraft takeoff speeds are calculated. So I just want to give you a very quick demonstration of how we calculate the aircraft takeoff speeds based on the weight of the aircraft. You can see we have 3,600 pounds in the left wing and 3,350 in the right wing. The reason there is a slight imbalance there is that after landing we were running the APU for about an hour, and the APU only takes fuel from the right wing tank. This is the total quantity displayed here. Now what I will do is just show you how we can balance that fuel manually. Up here is the wing transfer switch, and I'm going to select that to transfer from the left wing to the right wing. And you can see the schematic there is showing you fuel is being pumped from the left wing to the right wing. It's quite slow, so I will let that run while I explain the next part of the demonstration. Here I've put in the FMS a very simple flight plan from Sydney down to Melbourne. To calculate the takeoff speeds, we need to go through the performance initialization. per finit, and it then shows you the aircraft type and the tail number and the performance mode that the FMS will be using. We go to the next page. It talks about the climb profile, 300 knots into Mach 0.82. We cruise at 300 knots at low altitude or Mach 0.85 at high altitude. During a descent, we descend at Mach 0.85 into 300 knots. Going to the next page, we have our fuel reserve. Our company fuel reserve is 4,000 pounds. And we have the transition altitude of 10,000 feet. That varies around the world. In the US, for example, it's 18,000 feet. The speed limit below 10,000 feet is 250 knots, and I've just set up flight level 470. So at this light weight, the aircraft can easily climb to 47,000 feet straight after takeoff. I've put in a sample of 10,000 pounds of fuel. We can change that, but as you can see, it's showing you what the gauge is showing anyway, and for a real flight the fuel would match what is on the gauge. I've got 2 passengers and 200 pounds of cargo for a gross weight of 63,899 pounds. So now the transfer has been running for a few minutes. You can see there is now more fuel in the right hand wing, so I'll stop it there. Now that's quite normal before takeoff to have more fuel in the right wing, because as I mentioned, the APU is drawing from the right hand tank only. So generally you put the APU on an hour or 2 before takeoff, and that will then balance the fuel. Of course it doesn't matter in this case because the aircraft is going to be refueled anyway before the next flight. However, continuing down here, if we then go to our takeoff initialization, I've set runway 16 right at Sydney. You can see the length is 12,999 feet. I've put in an arbitrary temperature of 25 degrees Celsius and a wind of 160 degrees at 10 knots. Go to the next page. The runway condition is dry. We will have anti-ice off, and we will configure flaps and slats. Flaps at 6 degrees and slats out for the takeoff. We can now go to the takeoff data, and you can see the takeoff weight will be 63,649 pounds. The runway actual distance is 12,899 feet. The required distance is 2,913, so plenty of runway at this light weight. The important thing to note here are the V speeds. V1 is the decision speed. If we have any problems below V1, we will stop on the runway. Above V1, we are now going too fast to stop in the remaining runway distance, and therefore we must continue. In this particular aircraft, the rotate speed is usually always the same as V1. If the runway is wet, it can be slightly different, but in this case it is the same. So VR is the speed at which we pull back on the aircraft yoke and commence the liftoff. V2 is the most efficient speed to fly if we lose an engine. So if there is an emergency during the takeoff roll and we are above V1, we will be continuing the takeoff and we will aim to fly at V2. There's a tolerance up to V2 plus 10, but generally we aim to fly at V2. So we accept that. Now those speeds then get posted to the primary flight display. They will not appear at the moment because the aircraft is not in the correct configuration. The slat flap lever is currently at flap 0 and slats in. Now for takeoff it would be slats out and flap 6, and when that matches what we have programmed in the FMS, you will get the V speeds posted just here, just under that 30. So now let's take a look at how those V speeds change if we had a greater amount of fuel on board. notice them again. With 10,000 pounds of fuel on board, they are 98, 98 and 116. The VREF over here, also 116, that's the landing speed. We'll be landing at 116 knots, 50 feet above the runway, just before we close the throttles. That's the speed we're aiming for. So now let's take a look at an example with a much higher load of fuel. We'll go back to the perf and change the fuel load, but I just want to talk briefly about this V1 speed. Generally, it is the speed at which you cannot stop in the remaining amount of runway. However, in this particular example, the long runway at Sydney and the light weight of the aircraft, we could quite easily stop from 98 knots during the takeoff roll. However, the rotate speed is 98 knots, so at that point we have commenced the takeoff. So if there is any problem with the engine or the aircraft, once we have commenced the takeoff, we will continue. So the FMS has actually brought the V1 speed to match the VR speed in this case. You'll see when we put additional fuel on board, the V1 and the VR have increased significantly. So let's take a look at that. Let's go to the perf and let's put 44,000 pounds of fuel. Almost a full load. You can see straight away the FMS has said check your V speeds because they are no longer valid. The warning exceeds max landing weight. That's to be expected on a short 1 hour flight with full fuel. We would normally have a lot less fuel on that flight. We would only put full fuel on a long trip to, say for example, the Maldives from Sydney. Looking at the takeoff data now, we'll use the same runway, the same temperature and the same wind, and you will see that the V1 is now 131, again matching the rotate speed. So at 131 knots we commence our takeoff rotation. Above that speed we will not attempt to stop on the remaining runway. You can see that the V2 was previously 116 knots. It is now 141 knots, and that increased number is because of the extra weight. We have significantly more weight on board the aircraft with that extra fuel, and therefore you need more speed so that the wings can generate sufficient lift to carry the extra weight. If you fly too slow in any aircraft, you're going to stall and fall out of the sky. So as you can see, the fuel load on board the aircraft has a significant effect on the flying weight and the takeoff speeds.